Hello and welcome to the presentation about simplified DC circuit breaker models and DC circuit breaker test circuit. My name is Mario Zaja and I'm a research fellow at the University of Aberdeen. In the promotion project I contributed to work packages 6 and 12. My focus was on DC grid protection, namely DC circuit breaker design and modeling, as well as grid level protection studies where those same DC circuit breakers were utilized. This presentation consists of two main parts. The first part deals with the simplified engineering DC circuit breaker models for grid-level studies, while the second part demonstrates the DC circuit breaker test circuit, which was developed and used at the University of Aberdeen. So, on to the first topic, simplified engineering DC circuit breaker models. While performing studies of DC circuit breaker integration in mesh DC grids in Work Package 6, we encountered a problem. The problem was that the simulation models, which utilize a considerable but not particularly large number of DC circuit breaker units, took very long time to solve. To be more precise, we used a 4-terminal DC grid with 4 cables, so nothing excessive, and it required a total of 16 DC circuit breakers. For some DC circuit breaker topologies, simulating 1 second of this DC grid's response took well over 10 hours. This might have been faster had it been performed on a supercomputer, but these are the results on a typical office PC. I believe I do not need to explain why this is a problem. Another challenge we face is as changing between different DC circuit breaker topologies required making changes to the electrical circuit layout of the grid model. This made it somewhat impractical to compare responses of the same grid with different DC circuit breaker types. However, it really gets problematic in studies of realistic multi-vendor solutions where a mix of different DC circuit breaker topologies is utilized throughout the grid. For every possible combination of DC circuit breaker topologies, a separate grid model is needed. In our previous example, assuming 16 DC circuit breakers are used with 3 possible DC circuit breaker topologies for each breaker, the number of possible combinations rises all the way for 4096. To counteract the problems described, we developed simplified DC circuit breaker models for 3 DC circuit breaker topologies. The first topology is the hybrid topology shown on this slide. Compared with the fully detailed model, the simplified model replaces nonlinear semiconductor switches with ideal switches. Solving nonlinear circuits in electromagnetic transient simulation software requires a considerably higher number of calculations compared to linear circuits, so this change greatly reduces the complexity of the model. On the other hand, the modularity of the breaker model is preserved and all key functionalities are maintained. These include current breaking, fault current limiting, breaker self-protection, power loss estimation, arrestor energy estimation, and so on. The second topology we considered is the active current injection DC circuit breaker, whose detailed and simplified models are shown on this slide. Unlike the simplified hybrid DC circuit breaker models, the simplified active current injection model does not preserve breaker modularity. Therefore, estimating the voltage stress on each breaking unit is not possible. Nevertheless, most functionalities of the detailed model are preserved, including the current breaking, arrestor energy estimation, some failure modes, and influence of the injection circuit capacitor on the system. The third and final topology we considered is the VSC-assisted resonant current DC circuit breaker, or VARC. The simplified VARC model is identical to the simplified current injection DC circuit breaker model. The model limitations are the same, namely that the voltage stress estimation on individual breaker units is not possible. However, the other key functionalities are preserved, including the arrestor energy and power loss estimation, some failure modes, and parallel capacitor dynamics. In addition to simplified models which are unique to each DC circuit breaker topology, we developed a generic DC circuit breaker model which can be used to represent any circuit breaker topology. Of course, this introduces some limitations, as only the common functionalities of all breakers are preserved: current breaking, arrestor energy estimation, and some failure modes. However, the true power of the generic DC circuit breaker model is that the electrical layout is the same regardless of which topology it represents. Changing the breaker topology is made by simply changing the parameters of the model. The number of parameters the model requires is greatly reduced compared to the more detailed models. This is highly beneficial for preliminary protection studies since the researcher or engineer performing the study does not need to have in-depth knowledge of each breaker topology. This slide shows the DC grid test system used to compare the speed and accuracy of DC circuit breaker models. A 4-terminal DC grid is used, consisting of 4 cables and a total of 16 DC circuit breaker units. 1 second response is simulated for each DC circuit breaker topology and each model type, netting a total of 9 combinations. No changes are made to the simulation test case except for the changes in the DC circuit breaker model type or the model parameters. This table compares the response times of different DC circuit breaker models and topologies. Simulating a 1-second grid response using 16 detailed hybrid DC circuit breaker models takes an astonishing 11.5 hours. Using the simplified breaker model cuts this time down to 25 minutes, and using a generic model reduces it even further to only 2.5 minutes. The detailed active current injection model takes 6 minutes to simulate, while the simplified and generic models take 2.5 minutes each. The detailed arc breaker model takes over 3 hours to simulate, while the detailed and generic models take 2.5 minutes each, as with the active current injection DC circuit breaker. Evidently, there is a lot to gain by using simplified models instead of fully detailed ones for grid-level studies. This slide compares the responses of the detailed, simplified, and generic DC circuit breaker models. No notable difference is observed between either the voltage or current responses between the 3 models. Here are the responses for the active current injection DC circuit breaker. The simplified model produces a response very similar to the detailed model, but notable differences are observed with the generic model, whose voltage response differs considerably for one of the DC circuit breaker units. With the VSC-assisted DC circuit breaker, the differences between the models are more pronounced, particularly the voltage waveforms. The simplified model is more accurate than the generic DC circuit breaker in both the voltage and current responses. To conclude, simplified and generic DC circuit breaker models greatly improve simulation speed in grid-level studies. Response accuracy depends on the represented DC circuit breaker topology, and in this context, the hybrid circuit breaker benefits a most accurate response of simplified models. Generic DC circuit breaker model provides sufficiently accurate peak current and voltage thread estimates for preliminary protection studies, after which a more detailed model can be employed to improve the accuracy. And now on to the next topic. This slide shows the 5 kV DC circuit breaker test circuit developed at the University of Aberdeen's HVDC laboratory. The left side of the schematic shows the charging circuit. The circuit consists of a variac, a charging resistor, a step-up transformer with a transfer ratio of 15, and a diode bridge rectifier. It also contains a switch for connecting and disconnecting the charging circuit to and from the grid, as well as a switch for bypassing the charging resistor to achieve the highest possible output voltage. The charging voltage is regulated by the variac in the full range between 0 and 260 volts. The middle of the schematic shows the capacitor bank and the discharge resistor, which also serves as the voltage divider for capacitor voltage measurements. The capacitor bank is nominally 590 microfarads, but the capacitance can be increased to 983 microfarads at the reduced charging voltage. The right side of the schematic shows the discharge circuit, which consists of the fault-inducing thyristor and a freewheeling diode D5. The resistor RR is used to artificially increase the series resistance of the diode bridge rectifier and prevent fault current sharing between the rectifier and the freewheeling diode, since the two are connected in parallel. The RCB, DCCB, and the inductor represent the equipment under test. This is a demonstration of the test circuit discharging at 4 kV with the capacitor bank configured to provide almost 1 millifarad. A 4.8 mH inductor is connected to the DC side with no circuit breaker. Firing the test circuit provides a peak current of 1.8 kA, while the time to peak is 2.3 milliseconds. The exact current and voltage waveforms are provided on this slide. And this is the end of the presentation. Thank you very much for your attention. Hello and welcome to the presentation of DC circuit breaker failure mode. My name is Mario Zaja and I'm a research fellow at the University of Aberdeen. I participate in work packages 6 and 12. Since I already introduced myself in the previous presentation, I will just skip over this slide. Several distinct topics will be covered in this presentation. Firstly, failure modes will be introduced and classified. Hybrid DC circuit breaker failure modes will be studied, followed by mechanical DC circuit breaker failure modes, and lastly the energy absorber failures will be covered in a separate section. There are three types of failure modes: fail open, fail close, and fail while opening. Fail open mode means that the component becomes a closed circuit when it should be an open circuit. Fail close means that the component becomes an open circuit when it should be a closed circuit. Finally, fail while opening means that the component fails while transitioning from the closed state into the open state and consequently remains a closed circuit. All these failure modes are applicable to individual components as well as to the DC circuit breaker as a whole. The hybrid DC circuit breaker shown on this slide consists of 5 key components: the load commutation switch, the main breaker, the ultra-fast disconnector, the residual current breaker, and the energy absorber. In work package 6, we studied the causes and consequences of all 3 failure modes on each of the components. Some failure modes were studied analytically by means of literature review and computer simulations, while the others were studied experimentally in a combination of destructive and non-destructive tests. All this work is summarized in deliverable 6.6, but presenting it here would take far longer than the 10 minutes I have been given. Therefore, only a select few examples are chosen and presented here. Destructive experiments are of course the most entertaining ones to present, so I chose the test of load commutation switches surge arrestor failure. In this experiment, it is assumed that the ultra-fast disconnector failed to open because of actuator failure, or it physically opened but did so under current, leading to arcing. Whatever the cause, the UFD is not providing sufficient blocking voltage to protect the load commutation switch. Before the opening of the main breaker, the LCS's surge arrestor is visible as a blue button-like component. After the opening of the main breaker and the de-energization of the test circuit, the arrestor is visibly split in half. So the question is, what happened? This slide shows the current and voltage measurements across the load commutation switch. The red line on the left is the surge arrestor current. The red line on the right is the surge arrestor voltage, while the blue line is the voltage of the test circuit. Firstly, it is visible that the arrestor current continuously flows through the arrestor. This is fairly interesting because in the previous figure we have seen that the arrestor exploded and split in two after the experiment. As we all know, electrical current does not normally flow through air. However, the current can flow through the air if a dielectric breakdown occurs. This leads to an arc being ignited between the physically separated contacts. The arc voltage can be seen on the right image, and two things are noticeable. Firstly, the voltage is fairly chaotic with multiple spikes and dips. Secondly, the voltage does not resemble the current waveform at all. In a resistive circuit, we would expect the voltage of the component to be proportional to the current at any point in time. In other words, we would expect the two waveforms to have the same shape, only scaled by a constant. In this case, however, the voltage seems to be even slightly inverse proportional to the current, increasing when the current increases and vice versa. As stated earlier, the failure modes of individual components can be applied to the DC circuit breaker as a whole as well. By constructing a fault tree diagram such as the one shown on the right, a link between component and circuit breaker failure is established. In this example, a fault tree diagram of a hybrid breaker in open state is shown. The conclusions we have drawn from fault tree diagrams are the following. For the open circuit breaker to fail in a closed circuit, fail open mode, the residual current breaker must fail in addition to at least one more component. For the DC circuit breaker in the closed state, residual current breaker, ultra-fast disconnector, or the load commutation switch must fail to cause the breaker to fail in the open circuit. Lastly, the breaker will fail when opening if any of the components fail. Therefore, the breaker is most vulnerable to component failures at the same time when it is most needed, when a fault has occurred in the grid and the fault needs to be neutralized. By applying the same principles as with the hybrid DC circuit breaker, we analyze the failure modes of the mechanical DC circuit breaker. The mechanical DC circuit breaker shown on this slide consists of 4 key components: the vacuum interrupter, the injection circuit, the residual current breaker, and the energy absorber. This slide shows another experiment, the one that demonstrates the importance of firing the injection circuit at precisely the right time. The figure on the left shows the voltage and current waveforms across the vacuum interrupter during a successful interruption, where the injection circuit is fired precisely at 3 milliseconds. The figure on the right shows a repeated experiment in which the injection circuit is connected half a millisecond later. Despite the fact that the vacuum interrupter current is slightly lower at this instance, the interrupter's contacts have not separated sufficiently to block the generated counter voltage. An arc is ignited and the consequences are clearly visible, with the current declining solely because the test circuit capacitors discharged at around 13 milliseconds. As with the hybrid DC circuit breaker, fault tree diagrams are used to analyze the impact of individual component failures on the integrity of the whole DC circuit breaker. For a breaker in the open state, the residual current breaker plus one more component must fail to cause a breaker failure. For the breaker in the closed state, the residual current breaker or the vacuum interrupter and injection circuit together must fail in order to open the breaker. Lastly, any component failure will hinder DC circuit breaker's ability to transition from the closed into the open state. We paid special attention to the energy absorber failures because they are common to all DC circuit breaker topologies. The figure on the right shows the conventional energy absorber design, which consists of multiple parallel connected columns, each column consisting of multiple series connected surge arresters. Because of highly nonlinear VI characteristic, the failure of one surge arrestor unit draws more current into the affected columns, precipitating the cascaded failure of all the other surge arresters. If one column fails, the whole module fails because the main breaker is bypassed. However, the failures do not stop there, as the remaining healthy modules are forced to absorb additional energy. This creates a very vicious positive feedback loop in which a single surge arrestor unit failure may cause the failure of the whole DC circuit breaker. The figure on the left shows the absorbed charge per healthy arrestor unit in the faulty column, denoted by the blue line. The absorbed charge in the healthy column of the same module is indicated by the orange line, and the absorbed charge by the unit in another healthy module, which is connected in series with this one, is denoted by the green line. Dotted black line is the best case for charge absorption, where all is healthy, and the dashed black line is the rated charge absorption of the arresters. The failure of one single arrestor unit increases the charge absorption of that column by between 5 and 120 times. In such circumstances, the cascaded failure of the whole column, and therefore the whole module, is all but certain. At the same time, the failure of one module increases the charge absorption of the remaining healthy modules by a factor of 3. Clearly, there is a major flaw in the conventional energy absorber design because a single unit failure is highly likely to cause the failure of the whole DC circuit breaker. This should not be possible given the importance of DC grid protection for DC grid feasibility. To reduce the vulnerability of energy absorbers to single unit failures, a fully meshed energy absorber structure is proposed. In this layout, each row of surge arresters is connected by parallel interconnectors. When a surge arrestor fails, that particular row is bypassed on all columns while all the other rows remain inserted in the current path. As a consequence, equal voltage is applied across the remaining healthy units, which produces equally distributed current and energy absorption. This figure shows the absorbed charge per arrestor unit in the faulty column, the healthy column, and another module using the proposed energy absorber design. As it can be seen, the absorbed charges are identical, meaning that the charge is spread evenly throughout the absorber. We have also determined that, for a typical DC circuit breaker consisting of 4 modules, the absorbed charge of healthy modules in case of a single unit failure is below the rated charge when the number of series connected units is over 2. And this is the end of the presentation. Thank you once again for your attention.